welcome to this quote after dinner, unquote session of our Strings 2015 meeting. It's 100 years since 1915, and actually I'm extremely excited that the celebration of the 100 years of general relativity is being held during the time of Strings in Bangalore. So now there are some people here who actually put together string theory and quantum gravity, and so we thought it is opportune to have them reminisce about their work, which was done in the early 1970s. So with these few words, I'd like to invite Michael to take over the proceedings.
Oh, thank you, Spencer, and thank you very much for this fantastic meeting we're having, which must have taken a huge amount of organization. I'm not so sure if I'm thankful for this task. I presume I've been chosen for it because of my age, which, more than anything else. All I can say is that being old at least gives me the privilege of having lived through the beginnings of this incredible subject that we're all involved in. So I was a graduate student in the late 1960s, and the high point of my time as a graduate student was the paper that arrived from Veneziano in 1968, in the midst of a period when people just didn't know what they were doing with regards to our whole subject, effectively. There was confusion, to say the least, about the strong interaction and the weak interaction. And around me in Cambridge, people had essentially given up on quantum field theory. Ironically, this was the period when the Standard Model was just being developed by other people. But the huge influence came from the S-matrix effort, the bootstrap program. But out of this emerged Veneziano's paper, and that was stunning. Before Veneziano, there was confusion. After Veneziano, there was still confusion. But at least we had the idea that it was possible to write down an exact mathematical expression for the S-matrix, for the strong force, potentially. And so his paper laid the foundations for what later became known as dual models, and then morphed into string theory around 1972. And then shortly after that, the events which this session are meant to celebrate, I guess first in 1972, there was a realization by Neveu and Shirk that string theory, open string theory, has a deep connection with Yang-Mills field theory. And that was a very striking development that was underappreciated at the time, perhaps, but of course nowadays is at the center of what we do. And then 2 years later, in '74, these people, Yoneya and Schwarz, John Schwarz, together with Joel Shirk, produced their work on showing how the closed string theory is related to Einstein's theory of gravity. Again, something which, of course, was of enormous significance, but it was very underappreciated, I think, at that time. That was a time when many others who had been doing string theory were captivated by developments in field theory, which were, of course, equally remarkable. Not just the Standard Model being developed, but the advent of supersymmetry and supergravity, the topological aspects of quantum field theory, magnetic monopoles and instantons. All this was happening at the same time. It was an amazing time. And in the midst of that amazement, it was not clear where string theory was going, but nevertheless, these people had a feeling for it. So with those few words, I'm going to introduce the first of the two speakers, Yoneya.
Thank you very much. It is my great pleasure to be here to attend this wonderful conference. I want to thank the organizers for that, and also for warm hospitality, and also special arrangement of this after dinner talk. So organizers kindly asked me to give some historical reminiscences related to my old works on the connection of string theory with gravity. So let me talk about how I happened to come to this work as faithfully as I can remember now. Although I'm not sure whether such a personal history of myself interests you, but I hope that it at least would help to convey to you the new and now forgotten atmosphere at the genesis of string theory in the early 70s. Actually, I became a graduate student in 1969. And that was just the year when the string theory was born. At that time, string theory was called the dual resonance model, or in short, dual model. I vividly remember big excitement when I was first exposed to a very short but quite stimulating paper by Susskind on the string interpretation of the Veneziano formula. I was struck by the simplicity of the idea, giving a direct physical meaning on what was originally a mere mathematical expression, something like the Planck formula for the S-matrix elements of meson scatterings. And then I encountered a beautiful and more comprehensive paper by Nambu, and my interest was further strengthened. From a first encounter with the dual string model, basic question on the relationship between the dual model and ordinary quantum field theory was increasingly occupying my mind. Remember that the Veneziano formula originally emerged without any connection with field theory. There were two particular problems which I was concerned with. One was whether and how the channel duality, a so-called ST channel duality, could be compatible with the ordinary Feynman rules of field theories. Another was the meaning of the existence of massless spinning status. With respect to this second question, I expected that the dual model corresponding to open strings should be regarded as an intrinsic extension of local gauge field theories. From this viewpoint, I first tried to clarify the role of massless spin 1 state in the model by studying whether the interaction vertices of those states can be regarded as minimal interaction, just as we have in local gauge field theories, which are governed by gauge principles. My thinking was that if the interactions of these massless spinning states had non-minimal structure, the connection of the dual model with gauge principle would not perhaps be of fundamental significance. Actually, I could confirm indeed that in all cases of open string models which had worldsheet conformal invariance, the corresponding vertices could indeed be derived as a minimal interaction with an appropriate generalized local gauge transformation of a string wave function or string fields in an exact sense without any low energy approximation. Thus, I was convinced that the dual open string models must indeed be regarded intrinsically as an extension of gauge field theories. Needless to say, all these sound trivial from our present standpoint. But I would like to stress that as far as I knew at that time, around 1971, no one had ever formulated that explicitly, such a viewpoint. And when I first submitted a paper on this to a journal, it was actually rejected. After a few months of this experience, I came to know by a letter I received from Masatsugu Minami in Kyoto, telling that similar viewpoint had recently been discussed independently by Nouveau and Schauk, that paper you mentioned, in a different way, using a low energy approximation, namely the zero slope limit. I was shocked by this, and I immediately resubmitted the paper to a different journal. By this time, I actually hit an idea of extending my viewpoint to closed strings too. I thought the closed string model, which was called the Virasoro-Shapiro model at that time, should similarly be regarded as an extension of general relativity. However, In those days, the atmosphere of particle physics community was almost totally against general relativity. I myself felt that such a connection would be a rather strange and bizarre thing. Although, as an undergraduate student, I have been quite enthusiastic about general relativity, I myself became prejudiced against gravity after starting researches in particle physics. During that time, during that period, current algebra and its matrix were the major stream, at least in my environment, so that the classical geometric theories, such as general relativity, seemed to me to be useless. So I decided to put aside, oh, sorry, I'm reading this file. Yeah, okay. So I decided to put aside this problem of connecting closed strings to general relativity as a possible future work. And I turned my mind to the first question of reconciling the channel duality with Feynman rules. Minami's letter was useful for me also in that he mentioned Noboru Nakanishi's work. Nakanishi studied systematic method of decomposing integration regions of n-point duality amplitudes in such a way that each decomposed region involves only pole singularities corresponding to the usual Feynman diagrams. I tried to reformulate his rule of decomposition such that the factorization property of the amplitudes became manifest simultaneously. Then it would be possible to extend his rules of decomposition to general loop amplitudes. I partially succeeded in this problem on the basis of my previous works on Lejeune lattices. For example, this resolved the problem of infinite multiple counting, which had been a difficulty in the ordinary way of constructing non-planar loop amplitudes of open strings known at that time. And then I expected that the for loop could be recast as a quantum field theory of strings. I tried it very hard, but unfortunately, I couldn't do it in any satisfying way. As everyone knows here, this problem of constructing a covariant string field theory was beautifully achieved after 13 years by Edward Witten in 1985. Actually, the failure of constructing string field theory allowed me to turn my attention again to the possible connection of dual models to general relativity. I remember that was about the beginning of 1973. Around this time, many people, especially who are phenomenologically oriented, were departing from the dual string model. This was just a period when the gauge field theory were about to research at the fundamental theory of strong interactions as well as of electroweak interactions. But I felt that the dual string models must contain something deeper as a theoretical framework, which is perhaps beyond the field theory, and that has not yet been fully clarified. So I started thinking that as the Yang-Mills theory had turned out to be useful, general relativity might also become important for particle physics someday in some unexpected way. To demonstrate the connection, the first thing to do was to exhibit concrete correspondence of physical amplitudes and the zero slope limit, and also to make the comparison of interaction vertices with finite alpha prime. Another thing which I wished to clarify was to establish some definite correspondence principle between the two structures. I expected that there must be some characteristic property in analogy with the correspondence, for example, between commutation relations and Poisson bracket, which plays so important role in creating quantum mechanics. Although I am not completely successful, especially in the latter program of the possible correspondence principle, I decided to publish my modest results. The first paper was a brief letter which was submitted in July 1973, and then the full paper in October. The title of the full paper was Connection of Dual Models to Electrodynamics and Gravidynamics. The reason why I added the word electrodynamics was to discuss the similarity and contrast between the two cases of open and closed string in the simplest possible setting on the basis of my previous works in the case of open strings. In regard to the possible correspondence principle, I could only emphasize that the nonlinear geometric structure of general relativity were replaced by and encoded into the non-locality or extendedness of strings. That was discussed in my full paper by comparing the structure of the generating functionals for three amplitudes. And this interpretation of stringy extendedness actually constituted one of the motivations behind my later proposal of the so-called space-time uncertainty relations, which I first published in 1987 in a volume commemorating the late Professor Kazuhiko Nishijima's 60th birthday. In fact, in the meanwhile, I received a preprint by Schwarz and Schwarz. The paper was very impressive, and that actually stimulated me to continue my thinking further. In fact, after my initial papers, I published two follow-up papers discussing the geometrical properties of the couplings of graviton state to fermionic strings, extending the methods I had developed in the case of gauge string connection. I remember that at the time of the first publication of my results, I was, however, not completely sure about my standpoint in interpreting the connection between dual models and gravity. There was a different and competing viewpoint existing actually from the early 70s on the relationship between dual strings and the field theory, namely the possibility of strings emerging as a non-perturbative object from local gauge field theories. Among such possibilities are the so-called fishnet interpretation, and also later some relativistic vortices, as proposed by Sakita Birosolo in the first case, and in both cases by Nielsen Olesen. So I was asking myself, if such a view were correct, would it imply that general relativity could be contained in gauge theory without gravity? I had not been able to resolve this puzzle for many years. Of course, the holographic interpretation being developed in recent years is certainly providing us an entirely new perspective for this question. This was how I came to my early works on the connection of strings to gravity, and also some of my related thoughts during this period. Finally, as an aside, I'd like to remind you that this year is not only 100 years from general relativity, but also 150 years from Maxwell's monumental work with the title, A Dynamical Theory of the Electromagnetic Fields, which was published in 1865. This work can be regarded as the start of gauge field theory in the sense that Maxwell reformulated systematically and rightly his electromagnetic field theory in terms of vector potential by extending various previous works given by other people, most notably Michael Faraday. Actually, in the same paper, he also briefly pointed out a fundamental difficulty in extending his formulation further to gravity. So in this sense, he can also be regarded as the starter of the unification program. To conclude, I'm now convinced that the unification of gauge theory and general relativity as open and closed strings must be, at least in a broad sense, the truth of nature. nature must not fail to utilize such a simple and beautiful way of unifying fundamental interactions. Thank you for your attention.
Thank you very much for that presentation. And now for my long-term collaborator, John Schwarz.
Thank you. It's a pleasure to be here on this occasion, and I'm grateful to Spenta and the other organizers for giving me this opportunity. The ultimate goal of particle physics is to achieve a unified understanding of fundamental forces in particles in terms of beautiful and compelling mathematical principles. A closely related goal is to achieve a deeper understanding of the origin and evolution of the universe. These overarching themes were pioneered by Einstein. It seems appropriate to reflect on them in this centennial year of his general theory of relativity. With the wisdom of hindsight, we can say that his goals were on target, but that he did not have a realistic chance of success in his quest for a unified field theory. Crucial experimental and observational facts were not known at the time. Nuclear forces were poorly understood, and so he did not consider them. Also, his lingering doubts about the validity of quantum mechanics led him to focus on classical considerations. Let me now turn to the post-Einstein era, which is the one I have witnessed in my career. The strong nuclear force that binds quarks together inside protons, neutrons, and the other hadrons was not yet understood in the 1960s. During that decade, theorists faced the challenge of finding a simple explanation for the wealth of new particles that the experimentalists were discovering. I was a student in Berkeley, where professors Chu, Mandelstam, and others were developing ideas such as Regé-Pol theory and the bootstrap hypothesis. These approaches were not successful, but by a remarkable sequence of events, they led to superstring theory. In 1968 through 70, when I was a junior faculty member in Princeton, Gabriele Veneziano, Yuichiro Nambu, and others developed the dual resonance model, which was interpreted a little later as the theory of a relativistic string. This model incorporates the bootstrap and Regé ideas in a specific mathematical framework, and thus it was able to account for many qualitative features of hadron physics. In 1971, a second dual model was discovered by Pierre Ramond, André Neveu, and me. Both models shared certain defects. They required additional dimensions of space, and they predicted the existence of massless particles, which do not exist in this hadron spectrum. In the period 1972 to 73, several of us tried very hard to modify the string theories so as to eliminate the extra dimensions and the massless particles. However, all such modifications destroyed the mathematical consistency of the theories. The final nail was driven into the coffin of string theory in 1973-74 when quantum chromodynamics emerged as a theory of the strong nuclear force. Its successes were immediate and convincing. String theory, a very active area of research for about 5 years, dried up practically overnight. In 1972, I had moved to Caltech, and in 1974, I arranged a 6-month visit by Joël Schirk, a French physicist with whom I had worked earlier in Princeton. Both of us felt strongly that string theory was too beautiful a mathematical structure to be completely irrelevant for nature. We were convinced of the essential correctness of QCD, but we still thought that string theory deserved a last look before being abandoned. Soon we realized that its defects could be turned into virtues by using it for a purpose that is completely different from the one for which it was originally developed. Massless particles do occur in nature. The quanta of light, called photons, and the quanta of gravity, called gravitons, are examples. These particles are not hadrons, however. Indeed, all consistent versions of the string theories that we knew about contain a massless particle with exactly the properties of the graviton. By invoking prior results of Weinberg, we were able to show that the interactions of string theory gravitons at low energy agree precisely with those determined by general relativity. This result, as we just heard, was obtained independently, and a little bit earlier, I might add, by Tamiaki Yoneya. Also, we drew attention to the work of Kaluza and Klein in the 1920s, showing that extra dimensions of space can play a useful role in gravitational theories where the geometry of space-time is dynamical. Since I was trained as a particle physicist, gravity was far from my mind in early 1974. Traditionally, particle physicists were taught to ignore the gravitational force, which is entirely negligible compared to nuclear and electromagnetic forces under ordinary circumstances. For example, the gravitational attraction between an electron and a proton in a hydrogen atom is about 38 orders of magnitude weaker than the electric attraction. The physics world was quite different in those days. Physicists who specialized in the study of gravity, often called relativists, generally studied the largest things in the universe, including the universe itself, and they had no use for particle physics. They attended different meetings, read different journals, and had no need for serious communications with particle physicists. Just as particle physicists felt they had no need for galaxies, black holes, and the early universe in their quest to understand nuclear forces and elementary particles. For these reasons, even when Shirk and I realized that string theory had mathematical features suggestive of gravity, we were not predisposed to interpret it as a physical theory of gravity. Also, there was no community that was ready to hear about something like that. However, after a few weeks of intense deliberations, we were ready to take the plunge. Thus, Shirk and I proposed reinterpreting string theory as a framework for a unified quantum theory of gravity and the other fundamental forces. This was a radical change in viewpoint that required, among other things, supposing that the size of a string is roughly equal to the Planck length, even in order for the gravitational force to have the correct Newtonian strength. This is 20 orders of magnitude smaller than what was envisioned when strings were being used to describe hadrons, whose typical size is 10 to the minus 13 centimeters. In addition to incorporating gravity in a unified theory, there was another bonus. All previous attempts to include gravity in the framework of a quantum field theory had led to formulas plagued by meaningless infinities called non-renormalizable ultraviolet divergences. We knew that string theories have much softer, short-distance behavior than conventional quantum field theories, and we were confident that this problem would not occur. In short, we conjectured that string theory provides the correct framework for achieving a consistent quantum theory of gravity. Shirk and I were very excited about the possibility that string theory could be the holy grail of unified field theory. In addition to publishing our work in scholarly journals, we gave numerous lectures at conferences and physics departments all over the world. We even submitted a paper to the 1975 essay competition of the Gravity Research Foundation, for which we received an honorable mention. For the most part, our work was politely received. As far as I know, nobody accused us of being crackpots. Yet for a decade, very few experts took the proposal seriously. Fortunately for me, Murray Gell-Mann believed that I deserved to be supported. Being an environmentalist, he was concerned about endangered species. In 1979, Michael Green and I began collaborating on the further development of superstring theory. Each year we made discoveries that we felt would attract the interest of other physicists. This did not happen until after a discovery that we made in the summer of 1984 while attending the Aspen Center for Physics. We showed how certain apparent inconsistencies, called anomalies, are circumvented. The subject suddenly became very fashionable, one of the most active areas of research in theoretical physics. In the 60 years since Einstein's quest for a unified theory, the physics community has learned to accept quantum mechanics, and it has developed very successful standard models of particle physics and cosmology. Before we can bridge the gap between these models, which are valid at low energies, and superstring theories, which are best understood at the Planck scale, we probably need to learn facts about nature at intermediate energy scales. I think it is unlikely that the correct solution will be found by pure thought. A more plausible scenario is that our experimental colleagues will discover supersymmetry at the LHC. Since supersymmetry arose out of string theory, this would be an enormously encouraging demonstration of its relevance. If that should happen, the development of a supersymmetric standard model would become a realistic goal. Whether or not such a new standard model would be sufficient to point the way to the Planck scale, it would at least constitute a big step in that direction. In conclusion, the construction of the ultimate theory of all particles and forces based on superstring theory is still a distant dream. It can be frustrating when we are asked to make experimental predictions. Yet there are successes that we can point to. Our studies have led to very fruitful interactions with many areas of mathematics and physics. This is already compelling evidence that the string theory community is engaged in very important research. I feel very fortunate for having been able to participate in the development of this fascinating subject. Thank you.
I guess that's it.
Sorry, brief organizational announcement. This is about the Nityagram trip for spouses tomorrow. For those people who have signed up, there will be some sort of vehicle to pick up spouses at Fairfield Marriott at 9:20, Lalit Ashok at 9:25, Eco Green Park at 9:30. People will all be brought here, and then the trip to Nityagram will actually leave at 10:15 from here. Okay, so I'll just say the times again. Fairfield Marriott 9:20, Lalit Ashok 9:25, Eco Green Park 9:30. This being India with plus minus 10 seconds. Yes.
Just a minute. Hello, don't leave. I think this is a very opportune time for us to say thank you to the ICTS team actually that really has worked very hard to make this conference a great success. Please come here, all of you. Maybe I should introduce them to you. This is Mukesh. She's the Commander-in-Chief. Reena, Parul, Manasi, Madhulika, Rajlakshmi, Mayank, Srinivas, and Shishad. Please give them a very big hand. Thank you very much. Thank you.